Hello and welcome to the first video in my video series on partial differential equations. So I'll start with a definition, and that is a PDE is an equation relating the partial derivatives of some unknown function. So hopefully you've studied some ordinary differential equations already, and you know that an ordinary differential equation relates the ordinary derivatives. So when there's only one independent variable. Now we have perhaps many independent variables, and so we have partial derivatives, and the equation will relate those partial derivatives. Now oftentimes the goal when we study PDE is to learn something about this unknown function, and this unknown function we'll call a solution. And the solution is often something that we want to find an explicit formula for, or sometimes it's something we just want to know something about. We want to know some of its properties. Now, we will have three basic goals in our study of partial differential equations. Let me describe those now. So the first goal is one that's kind of easily overlooked, and that is to learn how to formulate partial differential equations. So what do I mean by this? Well, if you're studying some field of science or engineering, you often encounter some kind of dynamical process. You may be observing data from laboratory experiments, you may be deriving something from physical principles, but you're going to encounter a dynamical process and you're going to want to convert that into a mathematical description of the process. And that is the art of formulating a PDE, coming from a dynamical process based on perhaps laboratory data and writing down a mathematical equation to describe that process. So this is a very useful skill. The second goal will be pretty much the most obvious one, and that is to solve the partial differential equations. So that is to find the unknown functions that satisfy the relation that the partial differential equation describes. So we're going to spend most of our time doing this. We won't be able to solve every PDE that we encounter, but we will be able to develop techniques that will solve large classes of important equations, and so that will be most of our focus. Now, the third goal is to study the solutions to partial differential equations. Now, I don't necessarily mean to study the formulas that we get from part 2. Oftentimes we will have trouble obtaining formulas, or we may get formulas which don't give us a lot of information. And so we would like to have techniques for learning things about the solutions to partial differential equations without doing a lot of hard work to find formulas for the solutions. So things that we can learn about a partial differential equation just from the equation itself. I'll introduce now a little bit of notation that I'll use in the rest of the videos to be consistent. So for independent variables, I'll use things like x and y and z and t. So these will be independent variables. For dependent variables, I'll use letters like u and perhaps v if I have more than one. And I'll use subscripts for partial derivatives. So when I write something like ux, I mean the partial derivative of u with respect to x. Or if I write uxt, I mean the partial derivative, second partial derivative, with respect to x and then respect to t. Okay, so these be subscripts for partial derivatives. And one thing I should point out here is that I will use things like x, y, and z for spatial coordinates. So these will be spatial coordinates. And something like t will be time. We'll often have partial differential equations which describe some relationship between derivatives with respect to space and with respect to time. So right now we should just kind of get our feet wet a little bit by looking at a particular partial differential equation and examples of solutions to that PDE. So the equation we're going to look at is ut equals uxx. This equation is called the heat equation, and I'll explain in the next video why we would want to call it the heat equation. But for now, let's just take it as it is, ut equals uxx. Now I claim, first of all, that the function u equals 1/2 x squared plus t is indeed a solution to the heat equation. Let's check it. Okay, so check. How do we check? Well, we take this particular function and we compute ut and uxx and compare them and see that they're equal, and then it will be, we know that it will be a solution at that point. So first let's compute ut. Ut is the partial derivative of u with respect to t. Now that is 1, because the partial derivative with respect to t of t is 1, and the partial derivative of 1/2 x squared with respect to t is 0. Now we'll compute uxx, but first let's compute ux, and then we'll take one more partial derivative. So ux is partial derivative of u with respect to x, and that is, well, the t goes away because the derivative of t with respect to x is 0, and I get a 2 times 1/2 x, and so that's just x. So taking one more derivative, I get uxx, which is the second partial with respect to x. That's just 1. So checking that the heat equation is true amounts to checking that ut is equal to uxx, and this is simply the identity 1 equals 1. So we get a solution. So this is, we've checked that this is a solution to the heat equation. Now, just for fun, let me point out that this guy right here, this particular solution to the heat equation, this is called a heat polynomial. And the reason it's called a heat polynomial is because it is a polynomial in x and t, and it is a solution to the heat equation. There are many heat polynomials, and I challenge you to find another one, to find a different heat polynomial. There's many, and they're not that hard to find. Okay, now let's do something just a little bit different. Let's see if we can find a solution to the heat equation simply by making a guess. So this guess is often called an ansatz, and it's a little smarter than a guess. What it is it's an assumption that the solution has a certain form. So what we're going to assume is that the solution has the form e to the ax plus bt. This kind of an assumption is a lot more powerful than you might first assume, and we'll see that later. So what's the question here? The question is, what do a and b need to be in order for this expression to be a solution to the heat equation? So in other words, what are a and b? Or what relationship do a and b satisfy? Well, let's figure it out. So we plug it in to the heat equation. We have ut equals, well, it's e to the ax plus bt times, by the chain rule, the derivative of this inside function with respect to t. So we have partial of ax plus bt with respect to t, and that gives us simply e to the ax plus bt times b. Now we'll compute uxx, but let's do ux first. That gives us e to the ax plus bt times the partial derivative of ax plus bt, now with respect to x. And so that gives us e to the ax plus bt times a. And similarly, we would compute uxx to be e to the ax plus bt times a squared. So together, this information tells us that this expression, this function, will be a solution to the heat equation if the following relationship is satisfied. So ut equals uxx, which is the same as saying that e to the ax plus bt times b is equal to e to the ax plus bt times a squared. Okay, well, I can cancel these guys off. Let's cancel off this e to the ax plus bt. Now maybe I should say something real quick about that cancellation. these cannot be 0. If I exponentiate anything at all, I get something which is non-zero. So I am perfectly, it's perfectly legitimate to cancel these terms. So what I end up with is b equals a squared. So if you choose any a and b that satisfy this relationship, you get a solution to the heat equation. So for instance, a could be -1 and b could be 1, or they could both be 0. Or maybe a could be I and b could be -1. You think about that. All right. I'd like to conclude this introduction with a quick comparison of solutions to ordinary differential equations and solutions to partial differential equations. So this will be just a comparison by example, and a very simple one, but when you're just starting out, simple is good. So let's start with the ODE, which will be the population equation. Now this ODE is dp dt equals p. Frequently there's a constant in front of this p, and we're going to leave it off just to keep things simple. Now a general solution to this ODE is p of t equals c times e to the t. The c here is an arbitrary constant. And this is a thing that you see very frequently when you solve ordinary differential equations. You find arbitrary constants in the solutions. In fact, you often will find as many arbitrary constants in the general solution as the order of the ODE, so as the number of derivatives that you find in the ODE. Just one derivative here, so just one arbitrary constant. Now let's look at the same equation, but let's just make it a PDE. So we'll say a PDE that looks like the population equation. Okay, and what do I mean by that? Well, I'll just write ut equals u. And here we're going to assume u is a function which depends on more than one independent variable. So u depends on, say, x and t. Okay, so this is now a partial differential equation, and it looks very similar to this ordinary differential equation. Let's see what we can figure out about the general solution. So first of all, notice that if I take the function, so I'll say question mark, if I take the function u equals c e to the t, okay, so just like I took p, and let me be explicit that this is a function of x and t, so this is u of x comma t. If I take u of xt equals c e to the t, indeed this is a solution to this equation, because when I take the partial derivative with respect to t and I plug it in, I will find that I get a solution to the equation for any c that I choose. But you may ask yourself, why didn't I incorporate x somehow? I should be able to incorporate x. And if you think about it for a while, you realize that the partial derivative with respect to t treats x as a constant. So by plugging in x anywhere in this equation, it's essentially acts like a constant. So what I could do is I could take this c and I could replace it with any function of x at all. Okay, so let's call it capital F of x, where this guy now is an arbitrary function of x. Arbitrary function of x. So arbitrary function appearing in this general solution. And check it and make sure that you believe that that's the case. Take the partial derivative with respect to t and compare it to the original function. So here in an ODE I had an arbitrary constant. Here in a PDE I have an arbitrary function appearing in the general solution. Now this is not a general theorem, but this is a phenomenon that you will see very frequently. You will find arbitrary functions appearing in the general solutions. So this just gives you a basic idea as to what the difference is between solutions to ODE and PDE.